we subtract them. So we get some potential difference here, okay? If we don't have a potential difference, then we will not cause electrons to flow. It's similar to how we spoke about pressure. If pressure is equal, water won't flow or fluids won't flow. If potential is equal, the same thing. So we need a difference. Same way with gravity. I mean, we can keep going on and on. All right. So we're going to use the conservation of energy dealing with this. And before I even talk about that, I want to talk about what this resistor represents. It represents some kind of resistive load. Of course, it can represent this or this. This is a different kind of resistor. Or this. Here's a different kind of resistor. They look similar, but they all have different stripes. It can represent any one of those, but it can also represent the computer that I'm sitting behind. It has a bunch of resistors in it. It takes voltage to power this. A light bulb, all right? Your house, on and on and on. Your house has a whole bunch of resistances in it. And, you know, you have toasters, you have refrigerators. What it really means is, you know, they're using energy. That's really what it's coming down to. But any two ways, we're going to describe what resistance is going to do. So up here with this resistance, you're going to have a voltage that's associated with it. And you're going to also have a current that's associated with it. Current is going to flow around like so. And the first thing that I want to point out is that current is equal to current all the way throughout this circuit, because everything is in series. When I say it's in series, you have your battery, and then you have just a wire over here, which ideally won't have any resistance. And then you have a resistive load, which in this particular case is just our symbol for resistance. And then you have another wire over here, which is just, again, hopefully it has no resistance. But in every one of these scenarios, I is going to be equal. Okay. If I needed to write this out a little bit more explicitly, I could say I1, I could say I2, and then I could say I1 is equal to IR, or the resistance going through the current going through the resistor is equal to I2. That's really what I'm trying to illustrate right there. So we typically just call it I for I1 and I2. All right, moving on. Since we have that, let's describe the work. We talked about work, and work is just charge times the voltage. Okay. If we have, and I just want to minimize this for a second. If we have work here, then we can find power. So the change in work is just going to be the change in charge times the change in voltage. I could use the chain rule again, but let's just say that our voltage is not changing, okay? So this is what we have. If I put work over T, we end up with delta Q over T times delta V. So now what we end up having is I times delta V. This is just the current times the voltage. And that is the power. So we know that this is going to be in watts. We've already discussed power. Power is the same electrically, mechanically.